My name's Alec Pominville, and I'm a fourth-year mechanical engineering student.
Hi, I'm Will Rivet, and I'm a fifth-year mechanical engineering student. We're part of the Blizzard Baja Racing Enterprise here at Michigan Tech, and we're here to present our four-wheel drive project for this year. For our national comps this year, we've been required to build a four-wheel drive car. So our project this year is the implementation of four-wheel drive into our race vehicle.
So Will and I designed the mechanical aspects of getting power from the rear of the car, which we've done previously, to the front, making it four-wheel drive. Overall, we chose to use a drive shaft design.
Basically, the reasons we chose to do a shaft just like what you see in most normal road-going cars, is a much more standard option for us to implement, and it allowed us to compact a lot of our system to keep it in a fairly small package.
So we started by choosing what differentials we were going to use. So we're using the same differential in the front and the rear of our car. Once we source our differential, we were able to move back towards the center of our car. So then moving down to our drive shaft, designing a flange with our drive shaft that mates with the differential we purchased, and then going into the gearbox.
So we ended up running a full gear train for our gearbox. Once we had a general idea of the gear ratio that we were going to use, we were able to get our gear centers in our gearbox, and this allowed us to proportion our gears around our motor. And then once the gears were proportioned around the motor in the orientations we wanted them, we were able to design a case around that. Once the case was designed, we decided to do oil flow analysis on our case. We 3D printed all of the gears and the case itself. This allowed us to put a plexiglass backing plate onto that gearbox, fill it with the desired amount of oil, and then run that up with a drill. This allowed us to see our splash pattern throughout our gearbox and make sure that we're lubing all of our gears properly.
So our gearbox has two outputs, one to the front and one to the rear of the car. To size our drive shaft to the front of the car properly, we chose a 1-inch drive shaft that's 0.59 inches thick. That's got a critical speed that is more than 1.25 times the max theoretical speed of our drive shaft, as well as a factor of safety above 1.25, which means that our forces are not going to break it. After the U-joints, how we mate that with our differential is we have a flange. The flange also had FEA done on it. Our max theoretical torque was applied, and then constraints were placed at the bolt holes, and that also had a factor of safety greater than 1.25.
For the manufacturing of our parts, our team usually tries to build most things in-house, but for our project, our scope was so large, we did have to outsource some of our parts. So our gearbox case surround, and cover were all manufactured outside, as well as our gears. The assembly of our gearbox was pretty straightforward. We manufactured the shafts in-house. Some of our shaft dimensions did have to be modified to get the correct preload onto our conical gears that are holding our helical gears in. Once that was done, we had to go into manufacturing drive shafts.
So to manufacture our drive shafts, we ordered tubing, and then we made steel inserts that are welded into each end of the tube, which forms the drive shaft. The inserts have a keyway on them, which matches with our U-joints. On the other end of our U-joint, to mate with our differential, we use a 3-axis CNC mill to make a flange. The flange bolts to our differential, and then that's how we transfer power from our gearbox to our differential. So after we finished up our manufacturing, we began testing. This is important to validate all our analysis to make sure the forces that are going into our system are similar to the ones that we theorized. So to do that, we used a strain gauge on a front CV axle and a rear CV axle. These strain gauges have wireless transmitters, so then doing acceleration runs, we can measure the strain in both the front and the rear drivetrain, which we can then correlate to a torque going through our car.
So the results of our testing, we have realized that, we factored for almost no system loss, especially through our clutches. And in our initial tests, we are seeing a loss of approximately 40% of our expected torque through our system. This does not necessarily mean that these components won't see higher forces. We have not tested this car in a track environment yet, so when we do that later this semester, we may see higher drivetrain forces. Another thing that is going to allow us to collect more data for the team is there is an embedded data acquisition system in the car. This will give us data of the wheel speed, all four wheels, of the wheel speed of them, as well as shock position data of all four coilovers and engine RPM. That will better allow us to tune our suspension and our clutching, making our car more competitive at our competitions.
So beyond just the drivetrain, some other components needed to be redesigned in order to have a safe and competitive four-wheel drive car. So here to talk more about the braking system is Kiri and Kyle.
My name is Kyle Mayer. I'm a fourth-year mechanical engineering student.
My name is Kiri LeMahieu. I'm a fourth-year mechanical engineering student.
And for the brake system, we had to change from a 3-caliper system to a 4-caliper system because of our differentials this year.
Since our differentials have the capability of being open, we had to redo our brake calculations so that we had components that would actually brake the car properly. So this past semester, we went through extensive brake calculations, center of gravity calculations to determine what size caliper is actually required. Some additional changes that we had to make is we realized that the rotors we wanted to use were too thin for the specification on our brake calipers. What this causes is our piston to overextend, which can cause future issues or uneven wearing. So we added a shim to mitigate that issue.
For manufacturing the rear caliper mounts, we did some CNC work.
For a lot of the flat components, we had to get them either laser cut or water jet, and then some additional post-processing to make sure everything fit correctly. So in order to validate our system, we went through some acceleration runs and then made sure that the vehicle was able to stop in a straight line as per the SAE Baja rules.
We want to say thank you to GM for the General Motors Manufacturing Initiative, which supported us in manufacturing components for this car.
And thank you to the rest of our sponsors for building this vehicle.